So this is the first in a series of screencasts where I introduce some basics of hyperbolic geometry. The first screencast, my goal is simply to introduce the hyperbolic distance, what's called a Poincare metric. It comes from symmetries from complex analysis. That's the point of view I'll be taking. Let's look at it in a little more detail. First of all, we'll start with some very basic complex analysis, which is the uniformization. Well, what does the uniformization theorem says? Well, there are various statements, but I'll put a very simple one. So suppose omega contained in C is a domain and it's simply connected. Then omega equals 1 of, and here equals means equals in the complex analysis sense, biholomorphic. Well, it could be C itself, or it could be H, which is also D. Let me be specific here. H is the Z such that imaginary part of Z is greater than 0, the upper half plane, and this is the set of all Z such that mod Z square is less than 1, which is the open unit disk. Okay, so this is the subset of the complex plane this way or this way. So these are the two possible pictures. This is of course all of the complex plane. And so the uniformization theorem tells you any simply connected domain is one of these. Of course, deeper versions of this tell you given any Riemann surface, its universal cover is one of these. So this is really a very useful way of understanding complex numbers. Now this is Euclidean in a sense that I'll make precise in a few minutes. And hyperbolic geometry is important because this is hyperbolic. Now there is a third possibility if you are allowing a little more general Riemann surfaces. It may be the Riemann sphere. Okay, that is not actually the spherical geometry in this point of view, which is why I'm not going to talk much about it. But what we want to do is introduce hyperbolic geometry in terms of being the natural geometry on the upper half plane of the unit disk, which, as I'm emphasizing, are sort of very natural complex analytic objects. Okay, so well, in what sense is C Euclidean? So C is Euclidean in the following sense, namely, what are complex analytic symmetries? So biholomorphic maps, well, let me call them F from C to C. This means holomorphic and invertible. Now invertible in any given sense is the same thing. You can ask for it to just have an inverse as a set theoretic map that is being bijective, and then the inverse is automatically holomorphic, in particular continuous. Okay, so it's holomorphic and invertible are biholomorphic maps. These are exactly Euclidean similarities. Well, with one little caveat, which is that they have to be orientation preserving. Okay, so as we see in high school geometry, Euclidean geometry, there are really two ways of viewing it. You can view things in terms of congruences, which is preserving distances, or similarities, which preserve angles, or a better way of looking at it is preserve angles and scale distances by a fixed amount.